Okay, everyone, this is Unit 3 on polarity. Okay, so you've probably heard that term before in maybe in scientific context, maybe not. Polarity, polar, right? So like opposite ends, okay, like the North Pole, South Pole, bipolar disorder, right? Those things, they basically mean like opposite ends, okay? So how does that relate to what we're doing now? Okay, so by definition, polarity is an unequal sharing of electrons between atoms in a bond. Okay, now we're talking about an actual bond and the sharing of electrons. So remember that it's still a molecular / covalent bond. So this is a type, like a specific type of molecular bonding. So remember, what does molecular bonding? That's going to be non-metals, right? And they're sharing electrons. Okay? So this is a subset of covalent bonding. So we have the two kind of broad categories, right? We have ionic bonding and then molecular bonding. So just quickly remember the difference, right? This will be just a quick little review. Ionics are a metal and a non-metal. They are a transfer of electrons. And they do this transfer of electrons because they have a really large, I'm going to say delta electronegativity, meaning the difference in the electronegativity of the two atoms is huge, right? Because if you think a metal is on the left side of the periodic table, non-metal is all the way on the right, and the trend, obviously, for electronegativity goes up to the right. So they're going to have a very large difference in electronegativity, okay? So what that means is one of the atoms likes electrons so much that it literally rips the electron away from the other atom, creating ions. Now, molecular compounds, if you remember, are non-metals, right? But we now have two kinds. We can either be polar or non-polar. So polar simply means unequal sharing. Non-polar means equal sharing. So how do we know if it's going to be equal sharing or unequal sharing? Well, we look at the delta electronegativity. So you can actually look these numbers up. I'm going to show you the chart here in just a second. Delta electronegativity, if it's bigger than about 1, we usually say it's ionic. If it's somewhere between about 0.4 and 1, we say it's polar, most likely. And then if it's less than or equal to 0.4, that's kind of the cutoff, we say it's nonpolar. Okay? Now, these two are usually easy to distinguish because even if you're right on that like cusp of, difference of about 1, you can easily look to, does it have a metal or not? Because if it has a metal, it's probably doing ionic. If it doesn't, it's probably not. So that's pretty easy to distinguish between. Where it gets a little tricky to distinguish between sometimes is these guys. So you can kind of eyeball it usually and say, all right, how close together are they on the periodic table? If they're right next to each other, it's a tough call, but it's probably not very polar. If they're a couple boxes away, it's probably pretty polar. Okay, but you can confirm with these numbers. And I'll just show you what the chart looks like really quickly here. Okay, so this is an example of an electronegativity chart. Okay, and you can see, and we'll just copy this and bring this to our other page here. What you can really see here is 1, the trend, but 2, the actual values. So the trend, if you remember, goes up and to the right, right? So you kind of see the numbers trending there. And there's a handful of atoms that are super high, right, in that top right corner there. But you get the idea. Okay, so where do we go from here? Why do we care, I guess, is the next important question, right? Why does polarity matter? Okay, because it does quite a bit. So what this does for us is it allows us to determine, right? So you can determine the chemical and physical properties of a substance by knowing if it's polar or not. So like I can determine how reactive something is. I can determine how well something dissolves. I can determine, potentially the state of matter even, okay? So it's a very, very helpful thing to know. It helps us determine where the electrons are most likely to be found. Okay, and I'm going to explain that here. So we're going to look at 3 different compounds. We're going to look at NaCl, we're going to look at HCl, and we're going to look at Cl gas, okay, Cl to Cl. So looking at these, we have an ionic, we have 2 different molecular ones, and we're going to look at, are they nonpolar or not? So let me pull up another picture here so we can look at this. I'm going to copy that over. Okay. And we're going to look at how these things bond. So take a quick look at this. Now, we have 3 options. We have nonpolar, we have polar, and we have ionic. So what's the difference here? Look at these electron clouds. I want to start with the ionic one. Okay? Look what happens. Chlorine is so much bigger in terms of electronegativity. And if we actually crunch the number here, we're going to go back up to our chart. Cl has a 3.16, Na is 0.93. So like that's a huge, huge, huge difference, more than 2. So delta electronegativity is like super, super high. So what's going to happen is these electrons are only going to be found around chlorine and not around the sodium at all. Okay? And that creates a complete negative charge over here and a complete positive charge over here. Ionic, right? Okay. Look at the nonpolar now. Anything with itself is going to have a delta electronegativity of 0, right? So no one is outpulling anyone else. And so what we see is a very equal distribution of electrons, around the atoms. And we get no sense of charge whatsoever. So now we want to look at the middle here, the polar covalent, and look what happens. The delta electronegativity between H and Cl, right, was 2.2 to 3.16. So we're hovering right around that 1-ish, just under 1, right? So this is going to be about 1, which means this is a very polar bond. So what's going to happen is we get this sort of unequal distribution of electrons. The electrons are more likely to be found around the chlorine than they are around the hydrogen. And that creates these, okay? It creates the partial charges. That's what that symbol means, partial. It's not a full ionic compound. The electrons haven't completely transferred. Hydrogen is holding on just as much as it can to those electrons, but they're going to be more likely to be found around the chlorine. And so we end up with this unequal distribution, okay? Again, why does that matter? Why do we care, right? So this is what happens, okay? When you have something ionic, right, they tend to be in the solid state of matter, right? Like salts, crystalline salts. Because the charges, right, the opposite charges are so strong they hold the substances together, the ions together, right? They hold the particles, we'll say that's probably the better word, close together, right? You think of a solid, you think of like the atoms, you know, like this packed in a container, right? Okay, so what happens if you have something totally non-polar? So think like O2, N2, H2. Like what state of matter are they in? Well, they tend to be gases, right? And that's because there are no charges helping to hold particles together. Okay? There's no particles helping to hold these, or no charges helping to hold these particles together. So they spread out like gases. Okay? So that's, you know, sort of particles like sort of all over the place, right? So then what happens with polar? Okay? These tend to be liquids because there are partial charges holding the particles somewhat close, like a liquid, right? So they're kind of close. There's some level of attraction, but it's not quite enough to make it a solid, but it's pretty close, right? So that would be like water, okay? Hydrochloric acid, things like that, ammonia, okay? So the general thing that we want to take away from this is this thing called like dissolves like, okay? And that's sort of the mantra of biology, chemistry, in terms of polarity. And this is sort of a rule of solubility, if you will. And what it means is substances dissolve in other like substances. So in other words, things with charges like things with charges. Things without charges like things without charges. So what that means is things that are polar and ionic, right? We kind of say that those are sort of similar because ionic is really an extreme example of polarity if you think about it. So polar ionic will dissolve in other polar things. Okay? So in other words, things with charges attract. So this would be like salt and water. Salt dissolves in water. Salt is ionic, water is polar. This would be like alcohol and water. Those things mix because they're both polar. Non-polar things will not dissolve in polar things. So this would be like oil and water. As you probably know, those things don't mix. Or you could think of like nail polish. You put nail polish on, you can try to wash it off all you want, but the water won't take it away. What takes it away? Nail polish remover, because that is a non-polar solvent, right? The acetone will actually dissolve the nail polish. Okay? So that's kind of the general rule, okay? So let's do a couple of examples here. So HCl, we already kind of did, but if you look at this compound, how you would do it, if you sketch it out, right? We can look at our delta electronegativity, and if you calculate that, it should be 0.94, okay? So how do we represent that? Well, I would say the Cl is more electronegative, so that's where the partial negative charge is going to be. We can also throw back to physics, or I guess if you haven't had physics, this is a physics thing. You can draw a force vector showing which direction the electronegativity goes. So we would point towards the more electronegative atom. This is what we call a dipole moment. In other words, there's a polar bond in this molecule. Okay? All right, let's try HCN. You sketch it out, carbon in the middle, and you end up with this structure, okay? If we do the electronegativity, we're going to see that carbon to hydrogen, you have to do each bond. Carbon to hydrogen is 0.4. So we're right on the border, but we're equal to 0.4. So we're going to say that that's not really a polar bond. But the delta electronegativity between C and N is, in fact, a polar bond because it's about 0.5. Okay? So that is a polar bond. So now we want to draw our force vector. Well, it's going from the carbon to the nitrogen. And we usually put a little plus sign kind of at the end of the arrow to show that that's the positive end. So this molecule has a polar bond, and it's also a polar molecule overall. And I'm going to show you why that matters. Okay? So we have a polar bond, and we have a molecule that's polar for that. Okay, last one. CO2. We're going to draw this out. Okay? CO2. We're going to look at our delta electronegativity, and you can pause it and look at the chart if you want to. Just in the interest of time, I'm going to tell you. The difference is about 0.91 between C and O, which means these are polar bonds. So now be careful and draw the force vector. Well, this is a linear molecule here. So this is a linear molecule. And so we have these force vectors here. However, because this is linear, we have equal but opposite forces. So they cancel overall, right? They negate each other. So I would say CO has dipole moments, but is non-polar overall. And I can use my common knowledge to kind of confirm or deny this because I know carbon dioxide's a gas. And it wouldn't be a gas if there was any kind of polarity because the atoms or the particles would be attracted to each other. And they would be in more of a liquid type state. And that's sort of how I can confirm that. So it's important to find out, are there any polar bonds? Okay? Then once you determine that, you need to kind of understand the three-dimensional shape to see if these force vectors cancel out. Because if we look at something like water and we draw this out, and I say, okay, are these bonds polar or not? You should say, well, yeah, because usually hydrogen with pretty much anything is polar. But if we go back up to our chart here, oxygen is 3.44, hydrogen is 2.2. So yeah, this is hugely polar, okay? It's not ionic because there's no metal, even though the number might suggest that it's ionic. So this is hugely polar. So you got to draw your force vectors, but you have to be careful because water, if you remember, is not linear. It's going to have that kind of tetrahedral-like structure, which means we're going to end up with a bent structure for water. So our force vectors are going to be pointing towards the oxygen, but look at that. They don't cancel each other. They're almost additive, right? We almost end up with like a net force straight up, okay? They don't cancel each other out. So not only does water have dipole moments, but it is also a polar molecule, okay? Because those force vectors don't cancel out. So, to summarize, okay, what you're going to work on tonight is, or later now if you want to do it, there's a list of, I think there's like 7 or 8 compounds. I'm going to ask you if the compound is polar. So you first have to assess each bond in the molecule to determine whether the bonds are polar, and then you got to think about these things three-dimensionally and decide whether or not you think the molecule is polar, okay? Give that a shot. We'll see how it goes, and we'll regroup next week, okay?